Take a look at the molecule C3H4O3. In fact, this is an empirical formula, so I'll put the word empirical formula, EF, empirical formula. This would be measured in, for instance, in the lab. If you get measurements from a laboratory, experiment, where you know that for every 3 moles of carbon, then you also find exactly 4 moles of hydrogen within your experimental error, and also you find 3 moles of oxygen. Then the mole ratios, 3, 4, 3, go into this formula. But this formula may not be actually the molecular formula of the compound, because it's possible that the molecule actually contains a whole number multiple of what we have found here. So for instance, the actual molecule might be C6, in this case, H8O6. And this, in this case, is the molecular formula. So in the past, we've talked about the empirical formula, and now what you have to do in general is you find the empirical formula first, and then you figure out how to go from the empirical to the actual molecular formula. Now in this case, the empirical formula is exactly, or the molecular formula is exactly times 2. So 3 times 2 is 6, 4 times 2 is 8, and 3 times 2 is 6. And the reason that they can be different is because we don't have bionic eyes. We can't zoom in and look at the actual molecule that's in there to see what atoms are connected in the free-floating molecule. All we do is we stand back and look at trillions of atoms, and we find the mole ratios of all of the atoms present. So notice that the ratio 6 to 8 to 6 is the same as the ratio 3 to 4 to 3. You're going to get the same ratio no matter what. That's why we call this the empirical formula, the lowest whole number ratio of these atoms, whereas the actual molecule is this. I mean, look at just focus on the carbon and the oxygen. 6 atoms of each, right? So 6 atoms of carbon in ratio with 6 atoms of oxygen is the same as 3 atoms of carbon to 3 atoms of oxygen. The ratios between these elements are the same. So one more time, the empirical formula is the smallest whole number ratio. It's all it is. It may not be the structure of the actual molecule, it's just the smallest ratio of whole numbers that we get from the data that we have. But the actual molecule could be a multiple of that, depending on how it's actually constructed, but it will be some whole number multiple of the empirical formula. So how do we go from knowing the empirical formula that we get from measuring something in the lab to the actual molecular formula? Well, you need some additional information. You need to know something about the molecular formula that you usually get from other experiments. So let's take a look at problem number 1 and see how we would go from knowing an empirical formula to actually finding the molecular formula, okay? So problem number 1. Given the following information, determine the molecular formula for each compound. Now I have 2 parts. We're just going to read first part first. A compound with an empirical formula of CH2 and a molar mass of 84.00 grams per mole. So you're given 2 pieces of information. You're initially being told that the empirical formula is CH2, and you're also being told that it has that the actual compound has a molar mass of 84 grams per mole. In other words, that's the molar mass of the molecule, right? So you're given information about the empirical formula. Usually you would get that from experiments. In this case, we're just giving it to you. And then you're also being told the molar mass, not of the empirical formula, you're being told the molar mass of the molecule, basically of the molecular formula. All right, so the first thing we want to do, since we already know the molar mass of the molecular formula, let's figure out what the molar mass of the empirical formula is, which would be the molar mass of CH2, because this is the empirical formula. Okay, what we're basically going to do is we're going to figure out what the molar mass is of the empirical formula. We already know what the molar mass is of the molecular formula, and by dividing the 2, we can figure out how much more massive that molecule is, and that tells us the multiple we need to multiply by to change the empirical formula into the molecular formula. We have to get that number from somewhere, and we're going to get it by knowing the relative masses of these 2 different formulas, the empirical and the molecular. So how do we find the molar mass of CH2? It has 1 carbon, so that's 0.011 grams per mole, but we have 2 hydrogens, which is 1.008. This is in grams per mole, right? So for CH2, the molar mass of CH2, when you take 2 times this and you add the 12.011, you get 14.027 grams per mole. All right. Now this is the molar mass of the empirical formula, right? And we're already told what the molar mass of the molecular formula is. That's given in the problem statement. So what we need to do is we need to figure out what the ratio of these two things are. So let's figure out what is the molar mass of the molecular formula, MF, and let's divide it by the molar mass of the empirical formula. The molecular mass should be larger, equal to, or bigger than the empirical formula because they might be the same thing, but the molecular formula is usually more massive. It's either going to be more massive or it's going to be the same value as the empirical formula. All right, think about this example right here. In this case, this molecular formula is double the empirical formula. So we put the molecular formula on the top. All right, so what is the molar mass of the molecular formula? That is given in the problem statement. We have a compound with empirical formula CH2 and a molar mass. This means the molecule molar mass, molecular molar mass of 84.00 grams per mole. So right here we'll put 84.00 grams per mole. And we'll divide this by the molar mass of the empirical formula. We just figured out what this is, 14.027 grams per mole. All right. Now, whenever you divide these two numbers, 84 divided by 14.027, you're going to get 5.988. Now, the units cancel. You can have a cancellation top and bottom, so there's no units involved. This is just a ratio, and it's so close to the number 6 that we're basically going to say that basically the top, the molecular mass, is 6 times larger than the bottom. Yes, it's not exactly 6, but that's because these numbers come from experiments, so it's going to be basically impossible. I shouldn't say impossible, but almost never you will get whole numbers. If you take the decimals far enough out, then you'll have some decimals there. But when it's so close to a whole number, we can just round up and say experimentally it's very, very close to the number 6. So the molecular mass of this compound is 6 times bigger than the empirical molar mass. So what does this mean? This means that the empirical formula is equal to CH2. So the molecular formula must be, whoops, if I can put the thing right here. The molecular formula must be taking this guy and multiplying it by 6, right? So CH2 times 6, but that means I have to multiply all the carbons times 6 and all the hydrogens times 6, so C6H12. So the molecular formula is C6H12. That's the final answer. Now, this is the correct way to do things, but probably a little more professional way to write it would be if you know the empirical formula is CH2, and you really want to multiply it by 6, instead of writing it like this, which is kind of sloppy, what you can do is you can just wrap the whole empirical formula in parentheses and put a subscript 6. In chemistry, we know that when we group things in parentheses and put a subscript outside, it means that there's 6 of the grouping there. And it means that we have to multiply in to distribute in the numbers. So 6 times 1 is 6, and 2 times 6 is 12. If you want to write it like this, I think it's a little cleaner. If you want to write it like this, it's a little bit more of a layman's term. You understand what's going on. But you see how easy that was. Ultimately, what we have reviewed in the beginning of this lesson is that we have this thing called an empirical formula. We get it from the mole ratios of raw data. This may or may not be the same as what the actual molecule is. The molecule will be either the exact same thing as the empirical formula, like it is for water, H2O. The molecular and the empirical formula are exactly the same thing, right? Because we know water is actually H2O. CO2, we know the molecule is actually CO2. It's not a multiple of it, but sometimes there's a multiple involved. In this case, the multiple was multiplying times 2, right? To get from here to here. But we have to figure out when we're given an empirical formula to go to the molecular formula, what multiple to use. In this case, we just take the ratio of the molar masses, because that is going to be one way of figuring out how the two formulas differ from one another. You're going to need some other additional piece of information to go from empirical to molecular. All right, part B of this problem, we're going to find the molecular formula, a compound with an empirical formula of NH2Cl and a molar mass of 51.50 grams per mole. There's no trick question here. This is exactly the same process. We are given the empirical formula, and we're given the molar mass of the molecular formula, and we have to figure out how to go from one to the other. So the very first thing we need to do is we need to figure out what is the molar mass of the empirical formula that we have. So we're given that the empirical formula is NH2Cl. Let me just double check that. NH2Cl, right. So let's figure out what the molar mass of this thing is. We have one nitrogen, that's 14.007. I have some of these memorized, not all of them. If you don't have them memorized, just go to the periodic table. We have two hydrogens, that's 1.008 for each one of those. And we have a chlorine. Chlorine I don't have totally memorized, but you can go to the table, 35.45 grams per mole there. And there's only one of those chlorines, so I'm going to call it 35.453, carry one extra decimal. So NH2Cl, the molar mass of it, if we multiply this out, add this to it, and then add this to it, we get 51.476 grams per mole. All right, so this is the molar mass of the empirical formula. So again, in order to figure out what the ratio is, we have to find out what how much bigger the molecular mass is. And we know that we want to figure out what this ratio is. So let's figure out what the molar mass is of the molecular formula. And let's divide that by the molar mass of the empirical formula. Now we know what the molar mass of the molecular formula is given to us at 51.50 grams per mole. So we can write 51.50 grams per mole. And we can divide that by the molar mass of the empirical formula, which we just found, 51.476 grams per mole. Now the units completely cancel, so this is a dimensionless answer, 51.50, and divide that by 51.476, we get 1.00047. Notice that's so close to the number 1 that we're just going to say it's approximately equal to the number 1. What does this mean? It means the molar mass of the molecular formula is basically the same as the molar mass of the empirical formula. It's not bigger or smaller. It's not 2 times or 3 times heavier. It's the same mass as the other. So that means that in this case, the empirical formula is the same thing as the molecular formula because multiplying by 1 doesn't change any of the coefficients. So what the way you can write this, I guess, if you want to be a little more clear about it, is you can write down the empirical formula, NH2Cl. This is the empirical formula, and we can, since we know that the multiple involved between the two is just 1, you can just wrap it in parentheses and put the number 1 and basically say this is the same thing as NH2Cl. And this is the molecular formula. So I'll circle this, the molecular formula. In this case, the molecular formula and the empirical formula are exactly the same thing. All right? So in both cases, we needed to figure out some multiplicative constant to multiply the subscripts of the empirical formula to get to the molecular formula. That's the moral of the story. We're going to do more problems like that. But let's transition, even though the title of this lesson is all about molecular formulas, I want to do another problem where we're just finding the empirical formula, which we'll do next. And in the next lesson, we'll do some more molecular formula problems. I would like to read this problem to you because it also involves the conservation of mass also. So it's a little bit of a different flavor than the problems we've done in the last lesson just with empirical formula. Here we go. Mercury and oxygen come together to form 2 binary compounds. When samples of both compounds are heated, all of the oxygen escapes and the mercury is left behind. Given the following data, determine the empirical formula of each of these compounds. Now, what I'm going to do is write down the 2 different cases that we have. So we have basically a part A and a part B. Essentially, there's 2 almost totally separate problems going on here. I want to not worry about part B at all. I'm going to talk only about part A. So what we have is sample A has a mass of 0.64980 grams, and it says mercury residue from sample A is equal to 0.60180. So let's read the problem one more time, because in chemistry, reading the problem is really 90% of the actual battle. So we have to internalize what's happening here. Mercury and oxygen come together to form 2 binary compounds. What is a binary compound? Binary just means it consists of 2 different elements. That's it. Sodium chloride, that's a binary compound. Carbon dioxide, that's a binary compound. Binary just means 2 different elements there. It's not 3, not 4. And in this case, the 2 elements are mercury and oxygen. It says they come together to form 2 different compounds. So the subscripts could be different, but still they involve mercury and oxygen. All right, when these samples are heated, that means they undergo decomposition, then all the oxygen escapes. So the oxygen that was in the compound there, it just floats up and goes into the atmosphere, and there's a mercury left behind in the bottom. And then as this, given the following data, determine the empirical formula of the compound that was in there. And the first compound, sample A, has a mass of 0.64980. Mercury residue from sample A is 0.60180. What does mercury residue mean? It means I have the compound, it's got mercury and it's got oxygen in it in a vessel, and I heat it up and the oxygen all escapes. What has to be left behind? If the oxygen escapes and the only thing in the compound initially was mercury and oxygen, then what is left behind must be the mercury. The oxygen must have been what has escaped. So even though it doesn't say, it says mercury residue from sample A, 0.60180, that's what it says up here. What you know, because you know there's only two elements involved, is that must be the mass of the mercury left behind in the container. Another way to write this kind of mathematically is you can, I'm going to do this, the second one later. You can say that sample A, mass, is equal to the mass of the mercury residue plus mass of oxygen escaped. Before we do anything else, make sure you understand this. You have some sample A mass. It's a compound of mercury and oxygen. That's what we're trying to find out, the empirical formula for this compound. And when you heat it up, there's some residue left behind, which has to be mercury because the problem tells us that all of the oxygen escapes. But the mass of the oxygen that escapes, plus the mass of whatever mercury is left behind in the vessel, when you add them together, must be equal to whatever the original mass was because of why? The law of conservation of mass. We know that all of these compounds are made of atoms. If we measure the residue left behind, and if we know the residue is just pure mercury, and we know the original compound consists of mercury and oxygen bound together, then we surmise that the oxygen must have floated away somewhere. It has some mass, and the mercury left behind has some mass. We add them together, it has to be equal to the mass of what we started with, because nothing new was added to this thing. It just broke apart and was separated. Now, what is the mass of sample A? It's telling us right here, this mass is 0.64980 grams, right? What is the mass of the mercury residue? It says right here, mercury residue from sample A is this number, 0.60180 grams. All right. What is the mass of the oxygen escape? So mass of oxygen, I'll put mass of oxygen. That's what we don't know. And this equation, this law of conservation of mass, allows us to figure out what the mass of the oxygen is. Because remember the roadmap. In order to figure out the empirical formula of something, you need to know the masses of what is involved so you can find the number of moles, and the mole ratio is what we need to always figure out what the empirical formula is. So we have to work backwards. If we want to know the empirical formula of this, we have to know the number of moles of mercury and the number of moles of oxygen. But in order to know that, since we're given grams in the problem, we have to know the masses of everything. We know the mass of the original sample, we know the mass of the mercury left behind, we can calculate by subtraction the mass of the oxygen that floated away. How do you do that? Well, you do that by algebra. These are added together, so to figure out this, you just subtract it. And so what you say is that the mass of the oxygen left behind is 0.64980 minus 0.60180. So you just subtract this from both sides, and you get 0.04800 grams. So that's the mass of the oxygen. So the problem didn't actually tell us this, but now we know the mass of the mercury and the mass of the oxygen. Now, they are now separated from each other because it's undergone decomposition. But if we know the mass of the mercury after the decomposition, and we know the mass of the oxygen after the decomposition, then we also know in the original sample, those atoms are now combined into a compound. Those same masses of mercury and oxygen must be present in the same mass in the original compound, right? So because of that, we can then convert the masses of mercury and oxygen to moles. So let's start with the mercury. We know that we start with 0.60180 grams of mercury. How many moles of mercury is that? Well, we know that 1 mole of mercury is equal to what? You can go to the periodic table, find mercury. Sometimes it's hard to find. 200.59, right? I'm going to use 200.592 grams of mercury. And we cancel top and bottom. So what do we figure out from this? We figure out that if we take 0.60180 divided by 200.592, we get 0.00300. This is the number of grams of mercury in the original sample. Okay? Let's do the same thing for the oxygen. We now know how much oxygen floated away, and that means this many grams of oxygen must have been present in the original sample. 0.04800 grams of oxygen. And we have this one memorized, so 1 mole of oxygen is 15.999 grams of oxygen. Cancel, cancel. And so when we take 0.04800 divided by 15.999, we get 0.00300. Sorry about that, I have a mistake up here. This is moles of oxygen. This is not grams of mercury. The unit left over is moles of mercury. So this is moles. Sorry about that. Moles of mercury, moles of oxygen. So now we have everything we need to figure out the empirical formula, because the empirical formula, remember, relies on the mole ratio, the ratio of the moles, not grams, moles. And now we have them. But look, you can tell that they're the same thing. So you can already kind of surmise what's going to happen here. But let's go through the exercise. The mole ratio for mercury is 0.00300 moles of mercury. And what we're going to end up doing is divide by the smallest number that we have, but their numbers are the same. So really we're going to divide by 0.00300 moles. You could call it moles of the oxygen if you want to. And what you're going to have is a number 1. So you have 1 is the coefficient for the mercury, right? And you have exactly the same thing. I'm almost silly writing this down. But for the moles of oxygen, we're going to divide again by the same number, the moles of oxygen, because it's the same number, moles of oxygen. And what do you get? You get the number 1 for the coefficient of the oxygen. So for the empirical formula, the subscript for the mercury is 1, and the oxygen, the subscript, is also 1. So the empirical formula, whoops, if I can write correctly, sorry about that. The empirical formula, that's what I'm trying to write here, is HGO. So this is actually the empirical formula for this first experiment, for sample A. So if you have some unknown compound of mercury and oxygen, right, and you heat it up, and you know how much mercury is left behind in terms of mass, and you know the original sample mass, then you can subtract the two, figure out how much oxygen escaped in terms of mass, convert the mercury's mass into moles, convert the oxygen's mass into moles, and then do the mole ratio, and you can see that you have exactly the same number of moles of mercury and oxygen. That means the same number of atoms of mercury and oxygen. So HGO, 1-to-1 ratio, must be the empirical formula for the first sample. Now what we have to do for the next one is, it's very similar, but not quite the same. We're going to do the same thing again for sample B, but for sample B, we're now told that sample B has a mass initially in the vessel of 0.41720 grams. Now this one's a little bit different, because this one says the mass lost during the decomposition of sample B is 0.0160. So what does it mean when mass lost? This means that you take the mass of something beforehand, and then you take the mass later, and what we're being told here, after the decomposition happens, you basically weigh or take the mass before and after, and you figure out how much mass was lost. And after the decomposition happens, the oxygen floats away, and the mass of what is in the vessel left behind is less than it was before. In this case, it's telling me how much less, how much mass was lost. This mass, even though it doesn't say it here, has to be the mass of the oxygen that escapes, because the mercury is not going to float away. The mercury is heavy. It's very heavy, actually, so it's going to stay in the vessel. The only thing that can float away is the oxygen. So if the mass of the substance decreases, then that decrease must be the amount of oxygen that floats away. So this mass is the mass of the oxygen that floats away. So what we can do is we can do a similar kind of little equation here, where we can basically write down, let me just catch up to where I'm at here, where we can say sample B mass is it's the same thing. It's the mass of Hg, mercury residue, plus the mass of oxygen escaped. Now, the original problem tells us the sample B mass, and that is 0.41720 grams. 0.41720 grams, if I got that right. 0.41720 grams, right. And then we have the mass of the mercury plus whatever the mass of the oxygen escaped. So here it says the mass lost during the decomposition is 0.0160 grams. That has to be the mass of the oxygen. 0.0160 grams of oxygen. It has to be there. So we can use this to figure out what is the mass of the mercury residue left behind. All we do is subtract. We take the original sample mass, we subtract the amount of oxygen that escapes, and so what we get is the mass of the mercury that's left behind in that vessel. Take this number, subtract this one from law of conservation of mass, and what you get is 0.40120. 40120 grams. All right, so now we have everything we need. We have the mass of the mercury, and we also have the mass of the oxygen. So we just have to crank through the whole thing again. So let's do the mercury first. 0.4120. 0.4120, sorry about that, it's 40120 grams of mercury. Right, so we know that 1 mole of mercury is 200.592 grams of mercury. So we just looked that up in the periodic table, cancel grams, cancel grams. When we take 0.40120, divide by 200.592, then we get the number of moles, which is 0.00200 moles of mercury. Okay, so let's do the same thing over here. We have the mercury taken care of. This is the grams of oxygen. That must be what has floated away, 0.0160 grams of oxygen. We have that one memorized. We know that 1 mole of oxygen is 15.999 grams of oxygen. Cancel, cancel, so now we're going to have moles of oxygen. So you take 0.0160, divide by 15.999, and you're going to get 0.00100 mole of oxygen. All right, so now we have the number of moles of mercury and the number of moles of oxygen. And before you do anything, these numbers are very, very simple. So you can see that they're very nice numbers because you can easily calculate in our head. We're still going to do it. We're still going to write it all out. But you can see that the number of moles of mercury is exactly double the number of moles of oxygen. So you already know without doing anything that it has to be Hg2O. Right? Hg2O, because there's double the number of moles, double the number of atoms of mercury as compared to oxygen. So let's double check that. How would we do that mathematically? Well, what we do is we do the mole ratio for mercury. So 0.00200 mole of Hg, and we divide by the smaller number. The smaller number is the oxygen, so 0.00100 mole of oxygen. So what do you get? When you take these numbers and you divide, then you get the number 2. And this is the coefficient for mercury. All right, let's do exactly the same thing for oxygen. You're just dividing by itself, so 0.00100 mole of oxygen, and you're dividing by the same thing, 0.00100 mole of oxygen, and you get the number 1 for the subscript of the oxygen. So I'm going to wedge the answer right down below here. For mercury, Hg, the subscript is 2, and for oxygen, the subscript is 1. So Hg2O, this is the empirical formula. Yeah, don't like the way that looks. Something like that. You get the idea. Hg2O. Sorry about that. Hg2O, empirical formula. All right, why do we want to do this? Because we didn't do any molecular formula business with this. We did this. I wanted to do this problem because it's different enough from the other empirical formula problems we've done that I really wanted to make sure you understand how to apply the law of conservation of mass. That's really the only thing. If I just gave you the number of moles of mercury and oxygen, then you know how to find the empirical formula, no problem. But we have to sometimes do some subtraction. Think about the reaction. If it's binary, it's only 2 elements. If one of them floats away and one of them stays behind, then you can do subtraction and figure out what is left behind, how many grams of each. And then taking the grams and going to moles through the molar mass conversion on the periodic table, once you have the number of moles, then you find that empirical formula. So what I'd like you to do now is solve all of these problems. Make sure you're getting all the correct answers. Follow me on to part 2. We'll wrap up the concept of determining the molecular formula of a compound. Learn anything at mathandscience.com.